Welcome to this video. We are going to look at something called color mixing. The first note is that white light is not actually just one color. In fact, white light is a mixture of all colors in the visible spectrum, all mixed together in equal or roughly equal proportions. So we don't have just a single color that's white. You make it by striking all colors equally on the back retina wall of the eye. So when all colors strike that retina with equal intensity, we perceive that incoming beam, which contains all colors, we perceive it as white. And the same thing is true if we mix just the primary colors. So first, let me say the primary colors are red, green, and blue. These are the smartboard colors. They're the colors of the smartboard pens. So if you're in the test and you can't remember what they are, you just think about the smartboard or look at the smartboard if you're in that classroom, and you'll see the three colors right there. Yellow is not a primary color because it would be terrible to write on the board with yellow. So that's how you can remember. There's another way to remember what the primary colors are. They match the three types of cones. We have red cones, green cones, blue cones. And again, those would be L cones for long, M cones for medium waves, and S cones for short waves. So the three colors, primary colors, match the smartboard colors. And you don't have to mix all colors to get white. All you have to do is mix the three primary colors in equal proportions to get white light. So this bullet says when you get all colors together, they are perceived as white. And this one says when you mix just the primary colors, just the three, that is also perceived as white. So both are true. The three primary colors, we said, match with the three types of cones. Anything else here? And they match the smartboard colors, the pen colors. Okay. The next thing we're going to look at is color addition and color subtraction. If you take two primary colors, red and green, add them together, red light plus green light will form yellow light. So if two people shine flashlights, one red, one green, and they mix the two beams together, the resultant beam will look yellow to you. If you mix blue light and green light, you get cyan light. If you mix red and blue light, you get magenta. So these three things, yellow, cyan, magenta, are the secondary colors. And we can make colors by adding, or we can make different colors by subtraction. Here's what we mean. If you take white, white has red, green, and blue. If you subtract out the blue, all you have left is red and green, which makes yellow. Okay. If you take white light and let's get the next bullet. If you take white light and you subtract away the red, then all that's left is blue and green, and that makes cyan. And if you take white light and you subtract away the green, all you have left is red and blue. Red and blue mix, they make magenta light. So there are things called filters. And a filter is something that passes only specific colors. All of the rest are absorbed. A filter that is colored red only transmits red light. All other lights are absorbed. A filter that's colored magenta will not just pass, it won't just transmit magenta light, but it will also transmit red and blue, because those are parts of magenta. Those are the constituent parts of magenta. So magenta colored filters would transmit red, blue, and all combinations of the two. So now we're going to do some problems. We're going to solve some problems together to get a sense of how this color mixing is applied. Okay, here are the problems. The first thing I'm going to do is make a cheat sheet for myself. This will help me solve more quickly. So here we go. Green plus red makes yellow. Green plus blue makes, what's that, cyan. And blue plus red makes magenta. First question, says a white object is viewed under red and blue light. What color will the object appear? If the object is white, then it can reflect white light, which means it can reflect red, green, and blue. Now, the way it appears depends on what is actually getting reflected. So we're only looking at it under red and blue, right? In other words, whoops, here's how I like to solve these problems. I put a little check mark above red and a check mark above blue, because both of those will be reflected. Red strikes and is reflected, blue strikes and is reflected. So how does it appear? It appears red plus blue, because that's what's reflected, that's what hits our eye, comes back to us. And red plus blue is magenta. Okay, number 2. A blue object. If the object is blue, then it can reflect just blue. It is viewed under magenta light. So magenta light contains, what is it, blue plus red. So it can reflect blue. Is it reflected? Yes, because there is blue striking the object. The red does not get reflected. There is no plus red here. All that's reflected is blue. So how does the object appear? It appears as blue. A cyan object. Cyan. Oh, where's my cheat sheet? Cyan. That's green plus blue, right? So the object, the cyan object, can reflect green plus blue. It's viewed under green light. What color does it appear? Green light is being reflected. There is no blue light to reflect. So what color does it appear? Green. And lastly, a yellow object. What's yellow? If it's yellow, that means it can reflect green plus red. So let's come down here. Green, it can reflect green and red. It's viewed under cyan light. Aha! Cyan, if we look up, is green plus blue. Okay, this is tricky. So the green will be reflected. The blue will not. There is no plus blue here. All that it can reflect is the green and red, but there is no red striking it. So what comes back? What's actually reflected? This is what can be reflected. Appears is what actually is reflected. All we reflect is green, so it looks green. Okay, and we're going to do one final example. A magenta object. So if it's magenta, that means it can reflect magenta, and it can reflect blue and red. A magenta object is viewed under green light. What color will the object appear? Green light cannot be reflected. It's not in our list. That means it's all absorbed. All of the green is absorbed. Nothing actually is reflected back. So what color does it appear? If nothing gets reflected back, then the object appears black. So that's how you solve these problems.